How do you generate a key in DSS is Alice chooses the primes P and Q. The sender chooses E1 to be the qth root of one module P. Algorithm will be different, but the concept and the key generation methods will be same to attach to the new message that will be sent by the attacker, not by the sender, to prime values P and Q and empirical values E1 and E2. Hello students, welcome to the next session of network security. Let's continue this session with the same topic, that is about the digital signature. We know about how the digital signature is created with the help of a signing algorithm and is sent by the sender along with the message to the receiver, where the receiver runs a verifying algorithm to authenticate the signature or to check the authentication of the signature. If the algorithm returns the value true, then the message is accepted, else the message will be rejected. With this basic concept, let's move on to the digital signature's next concept, that is to know about what kinds of attacks can happen over the digital signature. In this, we have first thing is the key only attack. In this, the key is obtained by the attacker or the adversary and will try to use that signature along with some forged message to send to the receiver. Since it uses the key, it is called as the key only attack. Then we have the known message attack, where the message and its pair will already taken from the previous message. It is similar to the known plain text attack in the normal crypto system. The known message, which it is having the pair of signature and the message which was previously sent have been obtained by the attacker, and he'll use that signature chosen message as an attack. Message will be chosen which message to be attacked, then it will be forged with the signature. Okay. With that, we have two types of forgery also, where we forge the signature of the authenticated signature of the sender and sends a wrong message, or the unwanted message, or the message which affects the receiver system. In this, we have two types of forgery, that is the extensional forgery and the selective forgery. In this, the extensional forgery sends a message which is not useful, but it is a valid message signature pair where signature is authenticated but message is not authenticated one and is not useful even to the attacker. Just for the sake of attacking, he sends a message which is not used by him or which is not useful to him. It is vulnerable when, or it is dangerous when it contains some kinds of virus programs. It may affect the receiver's system, which is called as the extensional type of forgery. Then we have the selective type of forgery, where there will be selected messages sent by the attacker to the sender. It may not harm the computers of the or systems of the receiver, but it may be useful to the attacker in some other way. It may get some information from the receiver system and it may send it back to the attacker. But this type of attack is or forgery is very less possible because of various security methods that we follow. Okay. With this, we have different types of attacks. How to attack, avoid these attacks will be in this digital signature schemes. We have several digital signature schemes that use the concept of the crypto system itself during the last few decades. In that, some concepts are already implemented and some are theoretically proposed. Okay, let's see each of this. The first one is the RSA Digital Signature scheme. It is same as the RSA crypto system that we have studied in the third unit. The concept here is it uses the message, the signature, where in RSA crypto system there was no proof of any signature. There was no need of any signature. But the RSA Digital Signature scheme needs a signature, message, signature with two keys. The sender uses the public and the private key. We apply a function with mod n in the signing algorithm with message, the public key and the number of characters will be applied for the signing. When it comes to the receiving end, it will run, the receiver will run the verifying algorithm, uses the signature along with the private key and number of characters. So it will be with the sender to send the private and the public key. This will be congruent operation is applied over the received function along with the message. If it returns yes, the message will be accepted, else the message will be rejected. When you come to key generation in RSA Digital Signature scheme, we have the key generation is exactly same as the key generation in RSA, but here D is the private key and E and N are the public keys we use. When you check with the signing and verifying operation in RSA signature scheme, we have the signer which we use the Alice private key D with m to the power of D mod n expression we use to get the signature. S equals m to the power of D mod n we get. Along with signature, message is sent. Signature and message is received in the verifying algorithm. In a verifying algorithm in the receiver uses the expression S to the power of E, that is the public key, E is the public key, and signature to the power of E, S to the power of E mod n will be done, which calculates the m dash or m complement. Congruence operation is made on m dash and m. If it returns true, message will be accepted, else the message is rejected. How do you apply the RSA signature scheme on the message digest? So we use the hash function to generate a message digest. Okay. So this message digest is applied with the signing algorithm. Signing algorithm uses the expression S equals D to the power of D mod n. Signing signature is obtained and the original message is sent over the or transmitted over the network. At the receiver end, it runs the verifying algorithm, uses the expression D dash equals S to the power of E mod n, which takes the complement D dash. D dash and D are applied with congruent operation. If it returns true, the message will be accepted, else the message will be rejected. Okay, this is how the message digest is generated. Here we get again in verifying algorithm, the message digest is generated and is compared with the signing algorithm. Okay, so when the digest is signed, instead of the message, the susceptibility of the RSA digital signature scheme depends on the strength of the hash algorithm. How strong it is hash algorithm, the security will be more in case of the RSA digital signature scheme. Let's move on to the next one, that is LGL Digital Signature scheme. In this, we have the general idea of the LGL digital scheme. Concept is same, but the algorithm is little bit different in all these things. So we use two signatures in the LGL signature scheme, one message and two empirical values and one prime value we use as a public key, and D is the Alice private key and R is a random number we use. Random number changes with every new message in the network. Okay. So here we have the expression that can be used to signing algorithm. In the verifying algorithm, we use two signatures two signatures are generated in this. It will be used in the verifying algorithm to counter check or check the authenticity of the signatures. Okay. Now we use the congruent operation with the message as well as the signature. When it returns true, the message is accepted, else the message is rejected. How does the key is generated in the LGL Digital Signature scheme is, it is exactly same as the one used in the LGL crypto system. Okay. In LGL Digital Signature scheme, we have two empirical values and a prime value, which is a public key, and D is the private key we use. Okay. So here we have the verifying and signing diagram of the LGL system. Here we use the expression to get the two signs, one sign with a random number and an empirical value with the private key is applied. With this expression, we use the random number to generate two signatures and one message is sent to the receiver. At the receiver end, verifying algorithm is executed. It has E2 to the power of S1, S1 to the power of S2, mod P gets a version V2, and we use another one verification expression V1, verification expression V2 with these functions. When you perform congruent operation over these two verification expression, if we get the true value, the message will be accepted, else the message will be rejected. Okay. In this LGL scheme, one of the disadvantages, we use only single set of primes. To increase the security, you have to have long prime values, which increases or which decreases the execution speed of the signature schemes. To avoid that, an improvised method of LGL was introduced, that is the Snore Digital Signature scheme. Okay. Snore Digital Signature scheme again uses two signatures, S1 and S2, and a message M. Along with that, we have two empirical values and two sets of prime P and prime Q with Alice public key, which is a public key, and we use D as the private key and R is the random number we use in the cryptography or in the signature scheme. Okay. We use the function. In this, the modification is we use hash function as well before finally signing for the first method. Okay. We first apply the signature. Signature is applied. For the signatured message, we use the hash function, which generates a message digest along with the signature 1. So, signature 1 is used in signature 2 and is sent to the receiver. At the receiver, it is going to authenticate. After authentication, hash function is applied, which creates a congruence operation. Again, congruent operation is performed on signature 1 and the message. If it returns yes, the message is accepted. How does the key is generated in this digital scheme is, the sender selects a prime value P, which is usually 1024-bit long. Then the sender selects another prime Q, P and Q. So, the sender chooses E1 to be the qth root of 1 module P, 1 modulo P. So, we are doing the mod P over qth root of 1. Okay. So, Alice chooses another integer value D as her private key. Then she calculates empirical value 2, E2 equals E1 into D, the private key, modulo operation over P. Now she gets the public key as E1, E2, P and Q the expression, and private key is D. Okay. So we use the key generation. When you look at the signing and verifying in the Snore digital signature scheme, we again use the message. S1, S2 as the signature. We use V is the verification function. R is the random number. Then D is the Alice private key or the sender's private key. E1, E2 and P and Q are the sender's public key. Along with that, we have a concatenation operation. We have to concatenate the values, and H as the hash function. Okay, we will concatenate in this signing algorithm. We will concatenate the message with the signing algorithm. Message is concatenated with signing expression, and a hash function is run over the message to get the signature 1. Using this signature for this expression, we get R plus D is the private key into S1, sign 1. It is also an integer value we use. Mod Q will be done. Another set of prime is used. Another prime value. Modulo operation is done using the Q for second signature. These two are sent to the receiver along with the message. At the receiver end, you can view here again concatenated. Message is concatenated with E1 empirical value 1 to the power of S1, empirical value 2 to the power of minus S2 reverse with mod P, and a hash function is applied which gets the verification expression, verification value. It is made congruent operation with the signature 1. When it returns true, the message is accepted, else the message will be rejected. So signing, so chooses a random number R and calculates S1 equals hash function of M concatenated with E1 of R into mod P. Now calculates the S2 using the S1 value and gets the M, S1 and S2 which is sent to the receiver. Now the receiver calculates verification expression equals hash function of M concatenate with E1 to the power of S2, E2 to the power of minus S1 mod P. If S1 is congruent to V module P, the message is accepted, else the message is rejected. Now, let's have another scheme, that is the digital signature standard, which was proposed by the NIST in 1994. Okay, this is called as the digital signature algorithm and was criticized by the scientists, saying that it is not so much secured. What was the concept behind the DSS is, it combines the LGAMAL scheme, some concepts of the LGAMAL scheme and the Snore digital scheme. Let's know about the general idea behind this scheme. We have two signatures S1 and S2 and a message. Here we use two empirical values same as the LGAMAL, P and Q, which is a public key for the sender, and as usual D is the private key and R is the random number we use. Okay, so this is the procedure that we can follow for implementing the DSS. How do you generate a key in DSS is, Alice chooses the primes P and Q, uses the Z, the integer values with respect to P, prime value P, and set of prime values for Q. Then Alice creates the empirical value E1 to be the qth root of 1 modulo P. Okay, Alice chooses the private key D and calculates E2 equals E1 into D. Okay, Alice public key is E1, E2, P and Q, and her private key will be D. or the sender. Alice is nothing but the sender. Okay. How do you verify and sign in case of the DSS? So we use the message, the signatures, again S1 and S2, verification function, the random number, Alice private key, E1, E2, P and Q, Alice public key. We have the hash function applied on the message digest. What expression we use here? With the signing algorithm, we use a private key D with the expression E1 to the power of R, that is the random number, with modulus operation P. Over that, once again modulo operation is applied with Q to get the signature S1. Then we have hash function applied over the message with the private key and the signature 1 into R to the power of -1. Reverse will be done. Applying the modulo operation Q creates a message S2 and passes the message to the receiver. At the receiver end, we use this expression to calculate the message digest. We get the verification expression, verification value from this expression, which is made congruent with the signature 1. This is also in value, this is also a numeric value. When congruent operation is done over these values, and if it returns true, then only the value will be, the message will be accepted, else the message will be rejected. Next, we shall look at the concept of the DSS versus the RSA and DSS versus LGML. What is the difference? So, the computation of DSS signatures is faster than the computation of RSA algorithm because we use the same prime value, but the execution speed is more because of the expression we use, empirical value, and the congruence operation we use over DSS. When compared to LGML digital signature scheme with the DSS signatures or size of the signature are smaller than the LGML because Q is smaller than P. LGML uses only one set of value, that is the P prime value, which is 1024 bits, but we'll have P and Q which are smaller than the prime value. Okay, so they are smaller, but the capacity or the verification is LGML and DSS doesn't have much difference in the concept of or implementation of the keys. Okay. Next, let's know about the elliptic curve digital signature scheme. So, in this, the concept is same as the elliptic curve. We take the cubic equation, calculate the elliptic curve values, and we get the set of values to be as a ciphertext. Here, it will be the digital signature. But the thing is, here we use again two signatures as that of LGML and the DSS and a message with 6 values. So, we have 6 values A and B, 2 primes P and Q and 2 empirical values E1 and E2 which acts as a sender's public key. And as usual, D is the sender's private key and we have R the random number. Okay. Here you can view here functions are applied F1 and F2 to this function. Extract method is or extract algorithm is applied to extract the number from the function, extract a set of values for which mod Q, modulo operation by Q is applied to get one signature. This signature is used in another function to get the second signature along with the random numbers and the private key D and the message is sent. Here we use the function F3 from value the extraction algorithm is used, extract algorithm is used with modulo operation by Q, and the congruence operation is done on the two values, that is the signature 1 and the extracted value. When they are congruently true, the message will be accepted, else the message will be rejected. When you look at the key generation in elliptic curve digital signature scheme, the sender chooses an elliptic curve EP with the values, set of values A, B. Alice chooses, or the sender chooses, another prime Q with the private key D. Chooses set of empirical values E1, which are points on the elliptic curve. Okay. Again, using the E1 empirical value 1, the sender calculates E2, it is equal to D into E1 of set of values over the curve. Okay. Alice public key will have two values on the curve, two prime values P and Q, and empirical values E1 and E2. And her private key is D. We can use methods to calculate the signing and verifying. How does signing and verifying is done here? We use the message, two sets of signatures S1 and S2, random number, Alice private key D, use the verification function, then we use 2 points on the curve, the prime values and the empirical values, and we use 2 points P and T, that is P of U and V and T of X and Y, points on the curve. Then message digest will be generated. Then we get the intermediate results A, B. We use the expression here P of U, V equals random number into empirical value 1, set of values on the curve will be obtained, for which U mod Q expression message digest hash function will be applied, which gets the signature 1. Then we use the hash function over the message along with the private key into signature into random reverse of random number mod Q expression is used to get the signature value S2, and the message is sent. Here in the receiving end, the verifying algorithm uses ABT, that is intermediate results. A equals message digest, B equals both the signatures is used, and T, the intermediate values are obtained, for which a message digest algorithm is applied. We get the verification expression, verification value, which is compared with the value of the signature 1. If it returns true, the message will be accepted, else the message will be rejected. Next, we shall know about the variations and applications in the digital signature scheme. We have the time-stamped signatures. What is this time-stamped signature? Sometimes a signed document needs to be time-stamped. Why you need to make the timestamp is, at the time the signature is sent with the message, you have to have a timestamp. Once the timestamp is over, it's finished, the message, if it returns true, message will be accepted, else the message will be rejected. If you don't have a timestamp, the attacker may get this pair of message and the signature from the network and may modify the message and can send back to the receiver, and the receiver, when applies the algorithm on this set, pair of message and the signature will be authenticated. Authenticated signature we get. When you accept the message, it will be not the original message by the sender. So, timestamp is necessary to prevent it from being replayed by the adversary. We know about the attacks, replaying attack. It may be done by the adversary. To avoid that, we use the timestamp. This is called the timestamped digital signature scheme. Then we have the blind signatures. What does this will do is, there will be some applications where we'll have a document that we want to get signed by the sender without knowing what is the content of the message. Okay, revealing the contents of the message. Blankly, the sender has to sign the message and has to be transmitted over the network to the receiver. So this is a blank or blind signature that will be done by the sender. So this is about the digital signature schemes which can be using or which are using the previous RSA crypto systems, the LGAMAL crypto systems, elliptic curve crypto systems. All same concepts are used, but algorithm is different with signature schemes, two signature schemes, random numbers. Algorithm will be different, but the concept and the key generation methods will be same as the crypto system methods. Okay, so this is all about the digital signature. Thank you.